This is a weed whacker. It whacks weeds. So I'm going to give a very quick rundown on how it works, and then Sasha and Tomer will be going through a more in-depth explanation along with the math. Here's the flywheel, which is connected to the crankshaft and initially started by yanking this cord. The flywheel has magnets in it, which provide an electric field to the magneto that gives a voltage to the spark plug. The spark plug forces the piston to travel up and down by igniting compressed fuel and air, which we will dive deeper into. This weed whacker is operated by a two-stroke engine, which needs air and fuel to operate. A carburetor takes on the job of combining air and fuel to feed into the engine and ensures a proper ratio is met. A diaphragm pump is used to send the fuel to the carburetor. The piston moving up and down creates pressure changes in the crankcase, which in turn causes fuel to be pumped into the carburetor. There is a venturi within the carburetor that speeds up atmospheric air taken in from the outside by decreasing the cross-sectional area the fluid has to travel through. By the continuity equation, the fluid velocity must increase in order to conserve mass flow rate. Due to Bernoulli's equation, a pressure drop occurs, which pulls fuel along the carburetor and mixes it with the air to send to the engine. This engine, of course, is then connected to a shaft, which allows the weed whacker to spin.
So now we're ready to estimate our air-to-fuel ratio. Using our simplified carburetor model here, as well as Bernoulli's equation, now that we're assuming that this is in viscid flow, we can plug in the flow rate and also the initial kind of intake and mixing values for both the air and the fuel. And notably, the pressures cancel. The changes in pressure cancel because we're assuming they both start atmospheric and end up at some final mixing pressure. And so that makes our relation much more tractable because we're left with parameters that are either readily measured or looked up for air and fuel. So if we use the values we measured for the areas and then we use typical density values, we get a ratio of around 1250. And we wanted to compare this value with what an ideal air-to-fuel ratio would be for ignition, because that's what a carburetor is doing. It's preparing the mixture for ignition. So using typical stoichiometric ratio and converting that to a volumetric ratio using molar mass estimations and the same density estimation we've been using, we get an approximate 2000 ratio. And so we're in the right ballpark with our measured value, but it's a little different. And so we have a few postulates as to why this may have happened. In terms of assumptions within our model, we approximated the density and molar mass for a typical fuel, but the actual composition of fuel would have mattered, and we didn't have the actual composition. Additionally, for our model itself, it was probably somewhat actually viscid for the fuel, which would have meant that due to a loss factor, the speed would have been slower, and so the flow rate would have been lower, and so the ratio here would have been a bit larger. And that's probably what we're seeing here.
We rely on a number of engineering models and approximations to make our calculations that Sasha did earlier, namely the incompressible flow, steady flow, and viscid flow approximations and models. This is what allows us to say that the fuel and the air have a constant density, and that there are no viscous losses due to the Bernoulli equation, and that the flow is uniform along the streamline. All of these are what Sasha used for his calculations, and they are necessary to state and understand in order to know the system, essentially the power of these approximations. We're only going to be precise to a certain extent due to these approximations. If we wanted to investigate in further details what it would look like once we start breaking down some of these approximations, we can see what our losses may look like. Basically, using the iterative model that we described in Chapter 6, we start out with our delta P, our change in pressure, which is described as 2/3 of the atmospheric pressure in the textbook. We make a guess for our viscous dissipation factor, FD, and go down the line of all of the calculations that we did and the measurements that we did for the venturi. What we come is that eventually through the iteration, we converge to a viscous dissipation factor of
0.04. For the air, we undergo the same process, and we end up with a velocity of 630. Of course, using our Q equals UA equation, we end up with a ratio of air to fuel of 3,947. This is larger than what we had before, which makes sense because of the greater losses due to viscosity of the fuel.